Okay. So yeah, I'll turn it over to you, Clara, whenever you want to do introduction.
Okay, sounds good. Yeah, thank you. Thanks, Maggie, for arranging this. So today I'm pleased to welcome Mathieu Ratinsky, who recently has defended his PhD, which is focused on remote sensing of the atmosphere, specializing in atmospheric gravity waves and their interactions in the mesosphere, and even kind of extending throughout the upper troposphere, lower stratosphere region. So I've known kind of Mathieu informally for about a few months right now, because he's interested in doing postdoctoral work in the New York City area. And he really contributes something new with respect to especially the kind of observational capacity that we have for gravity waves. Just a little bit of context, one of the main difficulties in modeling stratospheric but also upper tropospheric circulations with respect to gravity waves is the lack of observational constraints. So some of the work that Mathieu has been doing, he'll be talking about, especially his work calibrating and validating the European Space Agency's Aeolus satellite data against lidar and radio sun measurements, will be particularly interesting to hear. Aeolus has been operating since 2018, and it's really the first satellite to provide global wind profiling throughout the entire troposphere and low stratosphere. So with that, we'll be excited to hear, Mathieu, what you have to say, and I'll pass it on to you.
Thank you very much. So yeah, a very good introduction. Globally, that's me, that's what I do. So I've been working on this PhD project for 3 years. I'm working at LATMOS, which is a French lab. I'm funded by CNES, the French National Space Agency. And as you just said, I've been working on Aeolus, and there's 2 sides to my PhD. One was calibrating and validating the data. And once that was done, I got to work with the data in terms of gravity wave analysis. So that's why I've decided to give the title of Tropical Dynamics in the UTLS, a new window with Aeolus. That's what I've mostly been doing. But I've also did some other studies that I will show you, more in the extratropical zones and trying different methods to see how it performs and what could be the better use in specific cases. I've understood I have around 40 minutes, so I'll probably show my most concrete and I guess grounded work first. And then I'll show you the more explorative parts, which could be more open to discussion and feedback. So if I have everyone in the room, I will begin. Do we have everyone?
Yeah, you can go for it.
Very well. So without further ado, I'm going to first present the instrument I've been working on, which is Aeolus. So Aeolus, as previously mentioned, is kind of unique in its state. It's a global wind profile observer. It was launched in August 2018 and finished its main working in April of this year. So that was a surprise because the initial mission was for 3 years. We actually got 5 years worth of data. So ALADIN comes with something that's called, the Aeolus comes with something that's called ALADIN. It's a Doppler wind instrument. This is new, actually. It's the first one to be in space. And with such a novelty comes expectations and challenges. You could name 3 of them. Where the biggest expectations lie would be improving the quality of weather forecast. We're going to see how Aeolus work, but basically it retrieves wave profiles over the first few kilometers of the atmosphere. So that's a huge improvement, as you said, in terms of observation. Also, that's a huge possibility to advance our understanding of atmospheric dynamics and climate processes through many observations and the possibility to assimilate and integrate these observations into models. But also, and I would think most importantly, it's a prototype, and it's a demonstrator for potential operational use of new similar ideas. And recently, I think beginning of this year, ESA actually accepted Aeolus 2 as a mission. So you can expect more babies coming from this area of research. So how does Aeolus work, generally speaking, and what does it measure? So when I will say Aeolus or ALADIN, it's more or less the same thing. ALADIN is the name of the wind lidar within Aeolus. So the way it works is you look at the first 30 kilometers of the atmosphere. What you have is a laser working, it's the lidar system. So what you do is you throw an incoming ray of light and you use the backscattering of the air molecules to get a receiving light on the other end. And through the Doppler shift, you can actually infer the velocity of wind, exactly like you would do with cars on the streets. So the base idea is this one, but then it's a bit more complicated since the satellite is moving and the polar orbits. What you have is integration of signal over specific distances. So Aeolus measures the first 30 kilometers of the atmosphere. It's difficult to go higher because then the density is very low and you don't have enough signal. But then in terms of track, it's around, as it says here, around 90 kilometers. And that gives you one observation. An observation is made of the sum of many measurements, but basically it gives you this average over a specific distance. It's also a bit complicated because, as you can see from the figure, Aeolus is not exactly in meridional or zonal wind. It's a mix of two that's called H-loss. H-loss varies in terms of the proportion of meridional and zonal wind. In the tropics, it's quasi-zonal, but the proportion can change over time, and that will be important to keep in mind further down the line. So that's basically how it works. So we use Rayleigh scattering, and I will focus on clear sky conditions, but keep in mind that we can also look at aerosols through mist scattering, and it has actually a wide array of studies, and I even got to work a bit on the Hungertunger eruption. So the first part will be mostly about when you get a new instrument, you have to know what it's good at doing, what are its blind spots, and I guess areas of improvement. We have the unique chance of LATMOS to have actually worked historically on lidars before, when LATMOS was called Service d'Aéronomie, and that's where we had this expertise of lidars coming from many years. We have two main sites, one in the south of France, in Observatoire d'Haute-Provence, and one in the French island of La Réunion, which is near Madagascar. That's very interesting, and I think that's what really helped this study, is that we had two very grounded sites at different latitudes and longitude, not very far from Aeolus overpasses. So we decided to conduct measurement campaigns. So to be more precise, the lidar we have, the grounded one, is exactly the same in terms of functioning principle. So it's this figure you can see here. It's the same bandpass, Fabry pair interferometer. I won't go into details, but basically there is no bias related to method because both use the same. The ground lidars can go very high, up to around 75 kilometers. So you are not restricted with the upper bound. And we decided to conduct 4 different independent studies called Above MIDO and Above OHP. The exact dates are here, but just keep in mind that we had the opportunity to do it at different times during the mission. So it was very interesting to see how the satellite evolved, because obviously it's a dynamic and living object. So you would expect some changes over time. And that's actually very important if you want to do some climatology further down the line. So what we did is a statistical comparison. And I think that's important to keep in mind because I will use this as a laying ground for the studies further down the line. So what we did was to directly compare lidar measurements with satellite measurements, but we also decided to throw radiosondes in the mix, which are very reliable, but usually doesn't go very far. So we had to take that into account. Keep in mind that with Aeolus, you would have ideally have wind from 0 to 28 kilometers. With radiosondes, it would be more 0 to 25. But generally speaking, what's interesting to see here, it's the mean bias over the altitude. The shading represents the spread. And as you can see, it's very interesting to see that there's a very obvious sweet spot in the middle, but it tends to have some deviation on the most lower part and higher part. So the lower part can be explained with what's called cloud contamination, which is actually very hard to remove. So generally speaking, even in clear sky condition, you would get some cloud contamination, explaining the discrepancies further down. And in the higher places, it's probably due to what's called a lack of density, so lack of backscattering. So that's where you have the signal to noise ratio that doesn't become very interesting, because you do end up having a lot of bias and random error that might not be actual physical signal. So we decided to determine a nominal range between, let's say, 5 and 22 kilometers. And we also had the opportunity to put that into perspective with what we call mission requirements that directly come from ESA. They have bias and standard deviation requirements. So we had the opportunity to check again. And in terms of bias, I would say it's pretty much respected, and this is good. But in terms of random error, it's a bit difficult. I would say it's around twice the expected one, which isn't terrible, but it's not mission requirements. So this is important to keep in mind, because this would have to be correct in one way or another. Also, one very important thing you can do when you do compare measurements is collocation and case-based study analysis. So what I mean by that is really a profile by profile comparison. Of course, you want to do at some point very large studies of large data sets. But here we had the opportunity to really pinpoint subsequent profiles between the ones seen from the ground and from the satellite. And we actually got to do some taxonomy of recurrent errors in some ways. So here you have, I guess, our very common usual suspects you would encounter. I think I'm going to start with the one that's on the top right, on B. So what you see is in red, you would see the ground lidar. So the red laser you saw in the picture. In black, you would see the radiosonde, and in blue, you would see Aeolus. Most of the time, if not always, the radiosonde and the ground lidar will always be very close together in terms of value and general trend. But it's very interesting to see that here, in this case, Aeolus tends to overestimate or just completely show different information in terms of the higher bounds. And after further verification, we think this is due to lack of backscattering. So as I said before, you have a very uninteresting signal to noise ratio. But what's interesting is that the shading here is supposed to be the estimated error. And as you can see, Aeolus is pretty bad at estimating its own error in the higher altitude. So that's something we have to take into account. And probably further down the line, we would have to restrict our study to maybe 20, 22 kilometers to not maybe fall into these kind of issues that might turn out to be false positives. The one on the bottom left is also very interesting. You can see a very good agreement, except for one point, which is this one. I won't go much into details, but that's what's called hot pixels. It would be the same as having a burnt pixel on your TV. This is a dark current issue we have. This is very common in accumulator instruments, where you can have a saturation of a specific point over time. So what you would see is actually in subsequent profiles of Aeolus, you would see the same point in the same place. It's kind of a burnt pixel. It is actually something we can treat and take care of, but over time it tends to augment. So the further down we were in terms of lifetime cycle, the more hot pixels there were, and that's also to take into account. And one last phenomenon, it's a phenomenon I've actually kind of discovered because I didn't see any literature before, and it opened up many conversations. So I had to choose a nickname for that. As you can see, there's a pretty good agreement, except you have this very oscillating pattern appearing. You could say it's hot pixels, but it should not be, in the sense that you wouldn't have just by random pixels that appear to be just on the opposite of each other. There is little chance of this happening. So we decided to coin it I2OP for instrument-induced oscillating perturbation. We have reasons to believe and prove that this is not coming from any physical signal, but from the instrument itself. And this is actually annoying, because if you are to expect gravity wave signal, they would pretty much look like this. So this is important to remove, once again, not to get any false positives. That was just to give you an overview of, I guess, what's important to keep in mind. But we also have some good news when it comes to Aeolus. When it comes to long-term validation, what we decided to do is to try and see if over time the random error tends to increase. So one way to do that is to look at Météo France data, so the national Meteorological Agency launches twice daily radio soundings over all over France. And we were lucky enough to be close enough to these radio launches each day. So what you have here is the standard deviation of the difference of one profile of Aeolus with one profile of a Meteo France radio sounding. So what's important is not really the absolute value, it's the change of this value over time. Since there's a lot of variation in wind, it's of course, you can expect a certain value of standard deviation, but you would not expect it to change over time because you would expect it to be similar. And what's interesting to see here is how over time it tends to slowly increase. So this is pretty good news in the sense that there is no drastic change in the data quality over time, but still you have to take into account a small increase. Also, you can see in red and blue, these were the measurements we took directly with our instruments during the campaign. So you can see that's why they are much lower, which makes sense. And we actually did this for both sides. So that's why you don't see the same values, but you do see the same trend, meaning that we have reasons to believe that this is a pretty reliable trend in terms of Aeolus. Okay, so that was for the Calvine part. There's a paper I did, which is quite extensive if you want to look into these details, but the core of my thesis and why I really got into this work is for the gravity wave retrieval, because as we said, I think it's a very important point to raise. Aeolus is new and has a lot of observations in places that we don't usually go, such as the tropics, and this is very new science in terms of data. But we decided to go with an approach of comparison. We wanted to use Aeolus, but also independent measurements from other data sets. So Aeolus, as I said, show wind profiles. It has roughly 1 kilometer vertical resolution. It's a dynamic resolution. I'd go in more details afterwards how it works, but just keep in mind 1 kilometer on average. And there is not at the moment a lot of assimilation by R5, which is interesting because we can actually compare two objects that don't really relate to each other. Then we have GNSS-RO, radio occultation, which is a method that through a current you communicate through two satellites going through the atmosphere. You can actually retrieve temperature information. So you do end up with temperature profiles. And that's also useful because wind and temperature can give you metrics that can be compared afterwards. But GNSS-RO is highly assimilated by R5. So it would be very interesting to see how assimilation of certain types of data can impact the result. And R5 shows both wind and temperature profiles that would be very convenient to do one-to-one comparison. It has a very cool vertical resolution, but it should be mentioned that the wind from R5 is not direct measurements. It's so-called indirect in the sense that you actually infer it from thermal information. There is no direct assimilation of wind at the moment. Okay, so what do I do in terms of gravity wave energy retrieval? We are focusing on kinetic energy. That's the main metric I will be using in this presentation. And you have to go through several steps. So when it comes to retrieving energy, you go through what's called detrending. The idea is to have a profile, such as this one on the left, which has a lot of variation, but you can't really tell if it's variation from a wave or variation from, let's say, the jet stream or general circulation. And you don't want to make false inferences. So what you have to do is understand what's the trend, what's the global movement behind it. You have two general ways to do it. The first one would be called vertical detrending. It's very straightforward. You just approximate the profile with a polynomial. It's very convenient because you just need any profile, you can apply the method. But the issue is that this is quite subjective, like what degree would I use? It tends to overfit. So the issue is that you would end up with a trend, but how can you be certain that this trend is representative of any physical or geophysical currents at the moment? So we went for another approach, which is called horizontal detrending. Horizontal detrending requires a lot of data because you're going to accumulate the data and you're going to create what's called an average profile or background profile in my case. So for this background, we decided to settle with a 5 by 20 degrees latitude longitude window over 7 days. So that's what you see here in red. the idea is that you have this general trend that encapsulates any major movements you had, and you have to remove that. What we do also is apply a low pass filter, because you want to remove everything such as Kelvin and Rossby waves. You want to really keep it small scale. So once you subtract it, you end up with this perturbation. That's the black dashed line. You apply a Welsh windowing to remove spectral leakage, and you apply then a filter, a high pass filter this time, to remove the rest of the perturbations, and you should end up with something that's pinpointed towards 9 kilometers, a bit more, a bit less. And you just square it, and you end up with the kinetic energy. After a smoothing, we decided to really focus on UTLS dynamics, so we had to pick a range, and the range is what you see in red, so that's the tropopause minus 1 kilometer up to 22 kilometers. So 22 kilometers, because as we said before, higher would be maybe a bit naive in terms of data quality. And tropopause minus 1, I think, is interesting, because usually that's where gravity waves really start to appear and expand. It wouldn't make a lot of sense to look much further down, at least for us. So I say kinetic, I'm talking about kinetic energy. I know the standard formula is this one, where you usually also have the vertical wind. So in our study, we do ignore vertical wind, and we don't really have very defined meridional and zonal wind. We have a mix, which is called H loss. So we come up with a new notation, which is EK H loss. It's very similar. You should not expect a lot of discrepancies. But of course, you should keep in mind that what we're showing is not exactly kinetic energy. There's a part of it that won't be shown because it's not detected by Aeolus. We could then talk a bit about more what's the ratio, but keep in mind that generally speaking, EKH loss is very fine for global representation. Also, when you talk about thermal information and temperature winds profiles, it's a bit different, but the method is exactly the same, and energy equation is quite similar. You end up with two metrics that can be compared very easily. It's the same exact method, same exact retrieval process. So there is no liberty taken on that part. And also one very important point before we get into the data is the noise correction. So as I mentioned, there's a small increase of noise over time, and we have to account for that. So there's two ways you can do it. The first one would be using error 5, which would be the red line you see here, or the other one would be using Météo France. As I've shown you earlier, we have many data sets. Both show pretty similar results, but we ended up choosing error 5 for one simple reason. The issue with Météo France is you have very localized areas of sampling. You can have La Réunion, maybe more in Africa, a bit maybe around the continents, but the biggest issue is you would have a lot of areas with no or at least a big scarcity of data. So it wouldn't be very wise, as you would not really encapsulate a global movement. You would only focus on local dynamics. So we decided to go with error 5, which I think is wiser when it comes to compromise between an accurate representation. It's also quite accessible. So it ends up being quite easier. And the use of that is the Aeolus estimated energy you can see in blue prior and after the noise correction, which is in green, and you have this very stable energy over time, which is marvelous when it comes to analysis. Okay, so now for the boring part is done, I'm going to go into the exciting part, which are the data. So what do we see? Actually, when I first saw the data, I was very skeptical because you never know what you might see. But I was very happy to find that data is quite physical, actually. So what you see is the kinetic energy of gravity waves from around 9 kilometers, more or less, in the tropics. And first of all, what's very interesting to see is that we have quite physical patterns. So what I mean by that is that you have clearly land convection over Africa. You have a huge point appearing in the center of the Indian Ocean, moving, it seems to be. You have also, okay, yeah, I'll just answer the question first. You said, how do I determine weights here? Actually, what I do is it's very easy to know the H loss value at each time if you know the coordinate. It's a projection. So I calculate the kinetic energy only through one value, which is U H loss, which is my mix of the two. But if I want to come back and say what would be the equivalent in either regional or zonal, it's doable through a method, but that applies a incertitude. So generally, we just keep this black box that is a mix between both components. The idea being that when we will compare with error 5, we will also apply the same projection, just to keep it on the same comparison scale. Was that answer?
Yeah, that was my question. And when you compare with the model, so somehow you're saying that there is information saved about the relative mixture of U and B from the satellite. Somehow that's information that's saved, and then that is what you apply to the model or the reanalysis.
Correct. Yes, exactly. Okay. Yes, that's true. So yeah, you could do the other way, which would be from Aeolus going back to regular U and B, but that introduces randomness and error. So the other way to do is we know exactly H loss values at each location. So you apply that formula to error 5, and you retrieve from error 5 EK H loss. I think it's you would be less inclined to errors that way, but both methods can be done. So you do end up with that very interesting pattern, which is recurrent over the years. And if you go to the opposite season, it's very interesting to see that you have this moving pattern shifting. And here you can see the monsoon region lighting up. You can also see permanent heat maps, heat places, such as land convection, as we said. Also here, maybe some orography. So what's the biggest takeaway from this is that you have consistent structures over the same season, which is a very good sign for physical signal. And also there's an actual symmetry seen between both opposite seasons, which is also something that is to be expected. We decided to compare directly with GNSS RO. So everything I'm going to show from GNSS and error 5 is also EKH loss. So it's projected, it's brought to the same mix of U and B. So as a disclaimer, of course, kinetic and potential energy are not a perfect one-to-one. There are debates. You could say it's 60%, 1.6. It's dependent on places and time and location. So it's let's just say you can do a one-to-one, but you can do qualitative analysis. And I think that in this regard, it's very interesting to see that for each period and its corresponding Aeolus period, you have the same disposition of pattern, which, hey, I think is quite a good result within itself, coming just from one information. And that's interesting to see, but we can actually push this further and look for error 5. So these are the results for a whole year coming from Aeolus. And this is what it looks like when you compare with error 5. Ta-da! So quite good. I would say it's a good first result to show in the sense that you have the same patterns. And once again, this is completely independent. There is no Aeolus in there, except maybe there's a small underestimation on error 5 side, or maybe overestimation on Aeolus side. But we have reasons to believe that error 5 is underestimating in that regard. We can also see the following year, which is also quite interesting in the sense that you have an increase of energy coming from Aeolus. This is probably due to a modulation by QBO. This is still to be determined, but it looks like there's a pattern similar to QBO appearances that might play a part in amplitude of signal. And once again, I would say that error 5 is in pretty good shape and consistency when it comes to patterns and general values. So that's nice. We could spend a lot of time looking at this, but I think the best way to do it is through Hofmöller plots. So Hofmöller plots are a very convenient way to look at such data. So what we decided to do is focus on the very equator latitude band, so -10 degrees. That's where you get most of the energy, and I think that's where we're going to have the most interesting conversations. So you can actually see the moving pattern from before appearing here quite clearly in the diagram. What you see is this longitude over time, so you can see the many different months of Aeolus use. Right next to it is error 5, and on the right is the difference between the two. It's interesting to see that, generally speaking, you would have a pretty good agreement, yet you have some underestimation from error 5. And I think this plot is particularly visual when it comes to explaining that. You can see that for very interesting events, you have this underestimation. And when it comes to what might generate these gravity waves, obviously the two options would be orography, which is quite possible, but over the tropics, I would maybe think more of convection and deep convection. And actually, there's a really good way to check that. You can look at what's called OLR, or outgoing long-wave radiation. And the thing is, the lower the OLR is, the higher the convection is. And we can actually plot the OLR on top of Aeolus to see if it fits. And voila, it fits quite well. And this makes us believe that what you are seeing here is pretty much convectively generated gravity waves. And what's very interesting is that that might actually be an underestimation on error 5 side, because there are much assimilation of such information in that area. Another way to look at things is to look at how GNSS and error 5 compare to each other. And well, I mean, it's no surprise they look alike, because error 5 assimilates GNSS. But when you look at OLR once again, you can see how it's very similar in terms of presence and patterns. So this begs the question, what if, because of the lack of assimilation in that specific area, both GNSS and error 5 tend to only resolve partially or just a part of gravity waves? And what I'm trying to do is that we don't have a good way of assimilating kinetic energy components of gravity wave in that specific area. And I think that's a miss from error 5. And that could be a very interesting way to integrate Aeolus results into broader models, would be a better representation of gravity waves in the tropics. Okay, so I guess that would be my biggest highlight in terms of work. It's my most grounded one. But then there's also the topic of dominant wavelengths, which is important to verify if you have any physical results. So what you're looking at here is the kinetic energy of Aeolus compared with the dominant wavelengths. We tried to retrieve the dominant wavelength directly through Aeolus' signal, but that's difficult to do. I will explain further down the line why, but we have something called RBS, or range beam setting, which is inconvenient because it's changing all the time. So it's difficult to have consistency. And generally speaking, we did not end up with a satisfying result. So we decided to do error 5 as a proxy. But having said that, it's very interesting to see that around the hotspots where you expect higher kinetic energy, so the lowest dominant wavelengths, it is indeed what you see appearing here. So once again, a proof of very physical signal, and beg the questions of what can be done with as information as this one, as good as this one. Okay, so that was the biggest part, tropics. Now we can think of broader studies, extratropical, maybe looking at orography. If we want to go through that route, we have to go through a bit more on Aeolus concepts, one being range bit setting, that I've mentioned a few times. So range bit setting, or RBS, is simply a name for vertical resolution. Vertical resolution on Aeolus is dynamic. It means that you can actually decide if you want to have a more dense setting, but that would mean you can actually cover less ground, or maybe you want to go with a wider approach, but then you have more coarser data points. So that's a compromise you have to do. And what they ended up choosing for Aeolus is to have this divided by latitude bands. With our company measurements, we had special RBSs where they would go actually as high as they could, so they could help our our lidar qualified Aeolus in the higher latitudes, but generally speaking, sorry, you would end up with latitude-specific RBSs. And this is annoying, specifically because what I'm going to show you for the tropics might not be true for the extratropics in terms of values, in terms of method, noise removal. It's a whole different topic because, of course, the data is kind of different. So this is what you get. This is what you get, and it's important. So I guess what I'm trying to say is, with a specific RBS, it's actually much more difficult to get data. And you can see that over the whole continent, it gets data that's indistinguishable from noise. It doesn't say that it's bad or unusable data, because of course, this can change with newer baselines. But at the time of my study, it was more cautious to just decide that this is a blind spot for him. But still, we can actually see some information appearing. You can see a lot of signal coming from the equator. And you can also see this very interesting spot appearing over Iceland that we might explore further down the line. So that's for the northern hemisphere. And southern hemisphere is also interesting because you have a lot of signal there appearing. So that raises a lot of questions. What do we see here? What does it mean? Why is Antarctica so lit up? So there were questions to be answered. And once again, we can come back to our independent findings. The resolution here is not the same, I apologize. But what you can see here is that it tends to follow general distribution. You have the same spot appearing over there. You could say that over below the Bering Sea, you have this general distribution appearing, but Aeolus has a harder time when it comes to comparing directly to Genesis in the northern hemisphere. In the southern hemisphere, it's also kind of strange. You have this very strong signal appearing, which you could argue is also seen here on the radio occultation side. But then you could ask yourself, why do we have this energy appearing here and not there? Could it be that this is mostly kinetically driven gravity waves, which is possible? Of course, we know that the ratio between kinetic and potential is changing, and this is even more visible around the poles. But I wouldn't expect something like this to happen. So what could it be? One way to look at things is to focus on this Greenland case that I think is very interesting. So I mentioned earlier I2P, maybe you remember them, it's this oscillating perturbation in the signal. I did a small program to remove appearances of these I2Ps in the signal. And would you believe that most of them are around Iceland? So I have reasons to believe that what we're seeing here this time is not actually physical signal, but more instrument-induced noise. So that's something to take into account. Is that it would seem that because Aeolus is in a polar orbit, maybe it's because you have more overpasses there. Could be many reasons. You have more errors in the extratropics. And actually, I'm only showing the northern version, but in the opposite season, you would see Antarctica lit up. So that would explain why you have such a high concentration of energy around these areas. But that doesn't mean that what we're seeing here is not physical. Okay, so I think that's the biggest takeaway from this study. We also decided to go through Hofmöllers once again to have a more global perspective. And you could agree that it tends to have the same general understanding of patterns. So I guess the trends are valid and legitimate, but it's harder, and you would have to go through more signal processing. One other thing I've also briefly mentioned is the noise correction, and noise correction is harder in the extratropics because of this whole zero signal line that kind of makes it more difficult to have a common ground for removal. And that's for the south, I guess. South is also quite nice. You can see this very visible signal here. This is the Andes and its orography. I would argue that Aeolus is quite capable of seeing it. But yeah, there's more room for improvement in that area. There are some patterns that can be seen, but it's more explorative at this point. And I wouldn't be as confident as to use them right away compared to tropics. One last method I can show you before I pass on to questions would be the gravity wave only method. So I mentioned this method of horizontal detrending, removal of trends, etc., etc. One thing I mentioned is I use a low-pass filter on the background. Actually, if you do that, that might be a mistake in some sense. I've been working with John Alexander on this, and she rose the topic that actually, if you do remove if you apply low pass here, the issue is that then when you will subtract the background to the low pass, you might actually introduce again Kelvin waves. And the biggest issue would be that it's true that some Kelvin waves, the small scale ones, are very present in the tropics. So this is a figure from Cao et al. From last year, and he actually, through thermal data, through balloons, he showed that there are Kelvin waves from around the same resolution in terms of time and scale in our data. So what John is inferring is that maybe, just maybe, what we were seeing before is a mix of gravity wave with small-scale Kelvin waves, and we don't want that to happen. In the extratropics, I don't think this poses a problem because it's mostly convective orography generated waves. So I wouldn't really mind, but I think this is non-negligible in the tropics. So we had to actually verify this. So we went with another approach, which is the no low pass. It's exactly the same as before, except you don't use the low pass in order to keep the Kelvin wave in the signal and then removing them when you subtract it. So we compared both methods. This is the method I showed you previously. This is the new one. You can argue it's more being cautious than anything else because you don't see a lot of change. But I think it's important because you have the absolute certitude that there is only gravity waves in your data. And we also decided to compare this with Arrow 5. So when it comes to Aeolus, I'm only looking here at a shorter time scale, but it's the same data. You can see it's fairly similar, although you go from around 30 to 20 joules per kilogram maximum. So that's interesting. It means that in terms of patterns, it's the same, but we could actually be estimating more than just kinetic energy of gravity waves because of Kelvin waves. So that's, I guess, one takeaway. But also comparing Arrow 5 with its former self, it's also similar. You do lose around 33% of energy, but you end up with fairly similar patterns and disposition, which would mean that either method or the other isn't really bad. I wouldn't say there's a better method. It's depending on what you want to focus on. Do you want to really see a general flow, small scale activity, or would you focus specifically on gravity wave? And I guess what I'm trying to say is you have method that kind of allow you to tailor your analysis to what you are looking specifically to implement. And sadly, when it comes to GNSS or thermal only information, you can see how, of course, when removing Kelvin waves, you tend to completely lose the signal and it's not really usable anymore. So I don't think comparing GNSS to Arrow 5 when using this new method really makes sense because you don't really see any more signal appearing in terms of potential energy. Okay, so conclusion. In terms of, I will start with the more explorative and open to feedback conclusions, and then I will finish with my, I guess, more grounded contributions that are already under review. So when it comes to extratropical studies, RBS, so this vertical range I've mentioned, is very crucial. Maybe I haven't stressed enough on that, but this is actually messing a lot with the interpretation of data, because this will change your maximum wavelength. It will change a lot of properties when it comes to signal capability and resolving capabilities. Also, the issue with extratropical is that you tend to have more I2Ps. That's annoying, especially when doing gravity wave studies, which are based around oscillations. So that's something to take into account. But I wouldn't be so negative, because I think you can actually make a lot of improvement on the second part, I2P, with the newest baselines. It's the issue they are aware of, they are working on it. And actually, the new and improved quasi-definitive baseline should come pretty soon, early next year. The RBS part, this is fixed and can be done, but I think there's a lot to do on the reprocessing of the data. Now, when it comes to the two methods I've showed, I think they both coexist and they aren't antagonistic. I think they can offer a different perspective on the same environment. Really depends if you want to be really strict on what you're looking in your signal, or you want to be, I guess, more explorative or more qualitative in what you're looking at. So that's what I was saying. Of course, the low path method might include short scale Kelvin waves, which might bias convective study regions. And the no low path method ensures only gravity waves, but then you have to restrict yourself to less instrument to compare it. It's a compromise, really. And when it comes to general conclusions, so mostly focus around tropical studies. So I think we can say that Aeolus is in really clear channel for retrieving kinetic energy from gravity waves through wind. Is feasible, is doable. I would argue so, and I think that what we're looking at is pretty physical, namely because the Iki patterns showed by Aeolus were shown to be consistent with one from independent instruments from either potential or kinetic energy. I would say that the hotspots we were looking at in the tropics were mostly linked to convective phenomena. I haven't mentioned this, but it's where the MJO, Madden-Julian oscillation, happens, and this was inferred from the OLR measurements I showed previously. Also, you can clearly see that error 5 reanalysis underestimates the kinetic energy regions where convection is higher. This is not the case for EP, as of course the model assimilates GNSS data. So you could open up the conversation by saying that I think utilizing Aeolus as a new data source to study convection-induced phenomena, especially in poorly assimilated tropical regions, would yield substantial scientific benefits to models, as once again, this is a place where this is where you would see the most increments in terms of data assimilation. And I think this is where science is to be made in terms of observational data in the next years or maybe decades. At least that's what I think. So thank you very much. This is my presentation. I hope you liked it. I'm open to questions if you have any. Thank you.
I have just a quick question, Mathieu. So the alternative method you were talking about in terms of removing the possible contamination with Kelvin waves, did that change any of the other conclusions? Because it kind of seemed like this came after the extratropics and the tropical experiments, or was this just the way you structured the presentation?
Okay, so initially when I did this whole analysis of tropics, John was already part of the project and we went with the first method. Around actually a few weeks before submitting, we realized that we had this possibility of having Kelvin-induced signal. And what's interesting is that none of the previous papers actually mentioned that issue. So we actually did the study again, at this time with the new method. And initially, the method we had also showed GNSS arrow, and we had to remove it. So the way I structure my presentation is not similar to how I would present my paper, which would use the new and more careful method, because it focuses on gravity waves. But then when it comes to what I did, I've used both methods, and I would be more confident in the second one, although in the tropics, it doesn't have a lot of impact. You would see the same patterns and you would see, generally speaking, the same values, or as I said, 33% less.
Okay.
But it's just that
Great.
for GRL, you have to be very focused and you have to be assertive. And I wouldn't want to use the first method when talking about gravity wave, because then I could get into tricky arguments where they try and you know, put me in a situation where I would have to explain that it's not exactly gravity wave and that there's some contamination. So I guess I went for the safe option, but both methods really work and show, generally speaking, a coherent pattern.
Okay, thank you. I think.
I'm sorry, I'm French. I tend to do very long answers.
No, that's totally fine. I think Claire, you also had a question.
Yeah. Yeah, thank you, Matthew, for a really nice talk. I think you've done a really nice job of highlighting, you know, the subtleties and the difficulties with the instrument and you know, the care that you have to take with it. So you obviously we've talked before, and I actually don't mean to digress too much into this, but you know, oftentimes from the modeling end of things, we would like to have observational constraint of the momentum flux. So perhaps it's possible that one might be able to obtain that kind of a measurement or infer that from the data, as you and I have kind of talked before. But I guess before that, so again, it seems like I'm harping on this, but it seems like that translation of U and V to H loss that you save, right? It seems like that also could be applied to the models. So in as much as you have an error of 5 to compare to, you could also apply that same those same weights to the model.
Of course, yes, that's the point. That's exactly the point. You can actually use any model you have that possesses U and V components and project it to H loss values.
Because those weights are just geometric, right? There's nothing
Correct.
else that would be.
The orbit is known, so you can tell exactly over a specific place what is the proportion of U and V. And you do have to cancel W. There's no vertical wind assumed.
Yeah.
And to answer the first question about vertical flux, I know, so I've been working with John and also Corinne Wright from University of Bath. They both asked the same question and are exploring the same question.
Yeah.
I would say it's possible. I've seen someone do something kind of similar with another project. And yes, you can retrieve momentum flux. I know it's possible, but that will require some studies. And as of yet, nothing is published of the matter. But that could be my next work. Who knows?
Yeah. Yeah. And sorry, just one more question, then I'll let others. So with respect to this is more of an interpretation thing. So then you speculate that maybe ERA 5 is somehow underperforming, at least relative to Aeolus, because it's assimilating the other observational data. But it could also be a model thing, I guess, right? So because the model has its own parameterizations and things like that. So have you actually done a test or is there a plan to test any kind of an assimilation of Aeolus in any reanalysis? It doesn't have to be ERA 5. I mean, do you know, I'm just curious, have there been plans to actually assimilate that data?
Okay, that's actually a very good question. And it's actually a question a reviewer asked. So that might have been you. But yeah, so the idea is to try and see if you could look at ERA 5 with Aeolus assimilated data. That's something we would like to do. So I've been talking to Michael Rini from ECMWF, and I think there's a product called IFS which assimilates Aeolus data. And we would like to probably do in the coming month some sort of studies on that. I wanted to, but that was exactly when I started to write my PhD. So I got cut into that. But yes, there is data that actually assimilates Aeolus from ERA 5. So ideally, my next slide would be with and without assimilation, and we could maybe see a difference. Yeah. And I think there is a difference.
Okay, thank you.
Okay, do we have any other questions in the room, or if anyone's online that wants to ask a question, please feel free to unmute yourself. No, just chickens. Okay, well, we are running a little bit over time. So I think maybe we can just end it there and then just give another round of applause for Mathieu for just a really great
Thank you.
presentation. Thank you. Yeah, and let us know if you're around New York at any time in the future.
Yeah, I'd just like to thank you all and just finish by saying that I'm finishing my PhD. I'm actually defending in December. And if you know anyone either at Lemont or Columbia, or more generally speaking, that would be interested in my work, know that I'm looking for a postdoc. So I will be very happy to show this to anyone that may be interested in observational constrained models. But thanks again for the opportunity, and I hope you've enjoyed this minute with me.
Yeah, great. Okay, thank you so much.
Thank you very much.
Thanks, Maggie. Thanks, Matthew.